सकते हैं सर।
Okay, good afternoon to you all participants. Today I'm talking about one of the lecture on concepts of GNSS, Global National Special System, or that is Global Navigation Satellite System, then IMU, and utility of it, as well as in LiDAR systems. What is the utility? Mainly the focus will be why GNSS and why IMU is to be required in LiDAR system. So before we see the utility, we will touch upon the understanding of GNSS as well as DGNSS, and then we will see how it can be used in LiDAR system. So if you see the very old and the very basic term given for GNSS was Global Positioning System, or GPS. With the time, if you see these positioning systems, in the Stone Age, people were using the attribute of the landmarks coming across in the sequence so that they can come back to their campsite or from the hunting site. And this system has worked nicely for small area, but when we are covering very large area, this system here in this system, the list of attribute tables become very large, and it is quite difficult to keep track the attributes coming across. Second, in the Star Age, when people were moving on the water surface, so there is no landmarks coming across, and so they have found to see above the sky, and they found natural stars. And using this natural star and the moon, they were able to locate their position through astronomical observations, and they called this as the Star Age system. And in this system also, when they are traveling very large area, different planets, different stars are visible from different locations of the Earth. And with that, the very high skilled expertise is required to use this planet position and calculate the position of their own. And not only the position, they have also used this system to get the time. Third age system came the radio age, in which people have tried to establish the radio stations, and they were transmitting the data. Objective was to transfer the data from one place to another place and to have communication purpose. But the positioning people have used this system of the Star Age, how to get the position at different locations. And you can see here, if they can monitor the signal is traveling from point A to a person, they can find out how much distance the signal is traveling. So once they know the range or the direct distance, they can get the radius of the circle, and they can tell the person can be standing at anywhere on the circle. And if they can get the simultaneously signal from two different towers, and these rays will intersect at point number P from two towers, or at point number Q from two different towers, and then they can pinpoint the person is standing at P or at Q. But in this case, if we introduce one more tower, so simultaneously signal is coming from three towers, and they can pinpoint where that person is. So that way the radio age gives you very pinpointing position. But here again, the drawback is at the regional level, the radio age system works fine. But when you go for globally, we have to put different towers at a distance of say 300 to 400 kilometers. So in that case, and we know that on the Earth only 1/3 is the land and rest is the water. So on the water surface also we have to put these towers, and it is quite becomes difficult task. So they have gone to the fourth stage called satellite stage positioning system, where it has a concept of radio age and the Star Age. In the Star Age, in place of using natural planets, they have replaced the natural planets with artificial planets in the form of satellite, and they have mounted these radio age as antennas on the artificial planets called satellite. So they are receiving the signals from the space, and they are getting their position. So here, if the three signals are coming from three different satellites, they will pinpoint that the person is standing at one point. So that way the system has been working globally nicely, and the name of the system has given satellite age, basically satellite based navigation system. People are using it. The system was initially developed for navigation purpose, specifically by USSR to know their defense vehicles on the ground, in the air or on the water surface. But today you see there are n number of applications. Wherever you can use the coordinates from GPS, that becomes application. And the three different segments in this are ground control segment, which is controlling all the satellites in the space, because this is not a single satellite system. You require large number of satellites, so they can transmit the data from ground to the satellite, and they can download the data from satellite to the ground. Once they download the data, they can see the health of the satellite, and does these satellites are moving in the defined orbit or in the reference orbit. And if some corrections are required, they can upload the data from ground to the space. So some minor corrections they can do. And if you see from satellite constellation to the user segment, it is a one-way communication. The user on the ground, in the air or on the water surface can receive the data and calculate their position and time. And there is no communication required between user and the ground control segment. If you see some examples of some of the specific GPS system, their space segments, like for USSR GPS system, there are minimum 24 satellites in 6 orbital planes, and there are 4 satellites in each plane. And the altitude of this satellite is around 20,200 kilometers, and with a 55-degree inclination from the equator. If you see further details of the system, they are separated. Each orbit is separated by 60 degrees. Total is 360. If you see the altitude from Earth center, it is 26,560 kilometers. The orbital period of each satellite is 11 hours, 57 minutes, and 57.25 seconds. And the velocity of the satellites at that altitude is 3874 meter per second. Ground control segment for USA-based NAVISA system is the master control, working as a at Colorado Springs, working as a monitoring station also, and some islands where they're also using them as a monitoring station of GPS satellites. Same for India. If you see for IIRS, they have the master control at Hassan, and other locations has been used as reference station. User segment can be at different ways, like it can be on the poles in the night time, on the water surface, in the air, or in the ground when it is raining. So in any time and weather conditions, the system can be used. So the system is time and weather independent. Then coming to GPS signals, there are a few type of informations we can extract once we receive the GPS signals. There are 2 type of signals we can receive. One is coarse acquisition CA, and second is precise P codes. And by these systems, and as well as there is satellite message information. And from this information, we can get the code measurement, where we are recording the time of the signal from satellite to the ground, and we can know how much is the direct distance or the range from satellite to the ground. In the carrier measurement, we are recording the phase information, and through phase we can again record how much is the distance there between satellite to the ground. And satellite message tells a lot of things: the distribution of the satellite in the space, their vertical elevation, horizontal elevation, and what different satellites are available in my particular study area, how they are distributed, so forth. Different type of instruments, if you see categorized, we can have, one is a multi-component GPS receiver, where you can see all the components are separately. One is a half kilo around battery. You have a control unit, you have a receiver, you have an antenna on a pole or on a tripod, and all are interconnected with the cable. Cost wise, or they are quite costly, and they have to be used in a pair as a base or rover. And there is a lot of advancements. There is not much cable connectivity is required nowadays. You can communicate through Wi-Fi or Bluetooth facility. And cost wise, these systems in a pair cost around 8 to 20 lakhs, depending upon what configuration you are asking or you're looking for. The first very basic category is handheld GPS. That means these systems are very small. You can hold in a hand, and you can get your coordinates. They generally work in port measurement technique, and here they work on the phase measurement technique. And here you have a small display device, some alphanumeric keys and the function keys to operate the device. These handheld GPS receiver can work with 1 to 6 pencil cells. Nowadays, these handheld GPS are outdated and no any companies manufacturing these handheld GPS receiver. But there are different versions of it which are available in the market. Further, you can see very old handheld GPS receiver from different company like Magellan, Garmin, and so forth, and further models from different brands. If you see the geodetic systems which are single or dual frequency, they can be a survey grade antenna, one control unit, one receiver, and one beacon. And they can be on a pole or you can put them on a tripod. You can have from different models of these geodetic GPS receivers. Generally, it can be of single frequency, or it can be of dual frequency, right? But from outside, you cannot see. Once you see its technical specification, then you will know it is single frequency or dual frequency. So these are the few commercial models which are available from different companies of single and dual frequency GPS receivers. Nowadays, you are getting a modified version of handheld GPS receiver, and which is called as nowadays mobile GIS GPS. And this type of version has taken a lot of modifications, lot of upgradations, and today you can see this concept in your mobile phone also. The advantage of using mobile GIS GPS is you can upload your study area image in the background. If you have a map, you can scan it, and again you can upload the scanned map in the background so that you can see when you're doing observations, you can see what are the different objects available on the ground through image or through scanned map. Previously, they were looking like one palm top was required, and then one GPS antenna which you can insert in the palm top directly with a card, and one software was required like ArcPad and so forth, which was running on these machines. But nowadays everything has been gone in one rugged machine, and you don't see physically the GPS antenna outside. It is already inbuilt as a small chip, and you can run by some software on the mobile phone. You can run through different apps available. Some apps are quite freely and some are paid. Coming to different positioning techniques you can adopt from GPS. One is single point positioning, and then you can compare it with the relative positioning. And you can have further categories, static and kinematic positioning, and real time versus post mission. We can see these positioning techniques one by one. This is your single point static positioning, and this is also called absolute positioning or point positioning. So here you are just going to a point and switching on your machine, and it is locking the few satellites available in your study area. And once you lock these satellites, you can get the coordinates of your ground. So it is single point static. When you're standing and doing observation and you're not referring any other point on the ground, this is called single point positioning. Relative means basically you have two units. One unit at point number, suppose lighthouse at point number 2, and one unit you have kept at point number 3. Okay, and what is happening here? At particular time, both the machines are on and they are working continuously, and they are recording the data, say every 1 second or 2 second rate. So what will happen? We can find out because the one unit is kept at point number 2, which is a known point, and we can find out, say, every 1 second how much is the error present in my coordinates. If we take care, the error at point number 2 and error at point number 3 is common. So we can apply error from point number 2 to point number 3 so that the coordinates of point number 3 can be improved. So this way it is called relative. So you can say you are improving the coordinates of point number 3 with point number 2. Kinematic, that means the point number 3 as a rover is moving. Real time means in the ground itself you are applying corrections from point number 2 to point number 3. and you can improve the accuracy of point number 3. So what is happening here? We are taking care of the 3 points, 3 observations, three conditions rather to be true. One is the observation rate of point number 2 and point number 3 same, that we can take care if both machines are recording the data at every say 1 second. Second is both are locking common satellites, that we can take care through mask angle so that both units lock the same satellites in the study area. And third is the baseline length from point number 2 to point number 3 should remain same, should remain 20 kilometer around, not more than 20 kilometers, so that the environmental condition at point number 2 and point number 3 remain same. Once we fulfill these 3 conditions, we can assume that whatever error we are getting at point number 2 at particular rate, the same error will be there at point number 3. Then we can apply the error from point number 2 to point number 3. So then what we say, it is relatively kinematic real-time positioning observations we are doing. Second case can be in a forest where we put one base station and it is connected with a tower to work as a transmitter, and it is transmitting the error in the given study area. So it is relative. Static means my rover is static and doing observation, and it is receiving the error through a beacon which is working as a receiving end. And real time, all these things are happening in the ground. Real time errors are transmitted from base to rover. But here rover is static and here rover is moving. That's the only difference. Then third case can be kinematic positioning and static positioning. So here basically the point is static and we are doing observations, and here we are moving and doing observations. So all these type of positioning techniques we can adopt in the ground as per our application requirement. Overall, you can see in the, if we have the beacon, we can do corrections from the ground, in the ground itself, from base to rover, real time. And if we don't have beacon and we don't have permission to use the beacon, so what we can do, whole day base is working at a known point, suppose on a lighthouse, and the rover is working at the different points. So we can download both data in a PC or in laptop, and then we can do corrections from base to rover with the help of a software. So this is called post-processing technique in the relative positioning. So overall, you can see different positioning techniques. It is least accurate is kinematic single point positioning. Then more accurate is static single point positioning. Then more accurate is kinematic relative positioning, and then more accurate is static relative positioning. So overall, you can see static and kinematic positioning techniques we can do in the ground. Then coming to GPS positioning errors, there are different type of errors, and before that we have to understand the difference of precision and accuracy. So precision means how correctly my observations are to the mean value, and accurate means or accuracy means how correct my observations are to its true value. That way, so you can have 4 combinations: precise but inaccurate, accurate but imprecise, imprecise and imprecise, inaccurate and imprecise, and here accurate and precise. So this is the best combination you can get. And with this, you can see the different errors present in the system, how correctly we are getting the satellite coordinate. That means the coordinates are how correctly mapped. Then the satellite clock, how correctly a satellite clock is giving time. Signal is coming through atmosphere. The 2 layers are playing very important role in this signal interaction. One is ionospheric layer, which is charged particle layer, and they introduce delay in the signal. And second is tropospheric layer up to our surface, up to certain height, and they have a water vapors and the dust particles. They also introduce delay in the signal. Then multi-path problem, that means there can be nearby object or tree, building, and we get the secondary signal received by the antenna. That is a multi-path issue. Then receiver noise, when the receiver is working continuously, the receiver get heated up, and once it is heating up, it may start misbehaving, and it may be introducing receiver noise. But nowadays they are quite rugged. They can run for a long number of hours, so still they don't introduce much noise in the signal. And then very important is how the antenna is set up, because antenna require leveling and centering, and that has to be seen. The antenna is set up perfectly. And then one more component is the receiver clock. How correctly the receiver clock is giving time. They are using a quartz clock, and their list count should be quite low. So here so many components are common, and we can remove through relative positioning between base and rover. Here you can see multipath and the blockage of the signal. If you are near to the building, one side of the satellite signal has been blocked, and in one case here you can see it is a direct signal and the primary signal, and you are also getting the secondary signal. So we should avoid the secondary signal. That means we should not do observation near to the building if you don't have any other facility to take care. Then if you see accuracy wise in different areas, the GPS gives you level of accuracies and the applications as per the accuracy. You may get say coordinate value 100 to 10 to 100 meters, then 1 to 5 meters, 0.2 to 1.5 meter, and less than 20 centimeter. So by this, there are around 4 level of accuracy you can achieve by the GPS, and then accordingly you may have application geomatics, land, marine, and airborne. In airborne, you can see one of the technology got birth, that is LiDAR, due to the availability or developed a technique called GPS. Then applications of GPS, you can see it is maybe applied in different areas. It can be agriculture, for precision farming, crop, duster navigation, tracking livestock, yield monitoring, so forth. It can be for mining, so that the big giant machines are moving to the accurate locations and digging to the particular defined area. It can be in the construction areas. Again, machines are very precisely putting the material used for construction. Then in public safety, it can be for police, fire, ambulance, and rescue and such. Basically, GPS can guide where are my ambulances, where are my police vans, where are my fire brigades, and we can place the order so that they can go very easily to the defined site where some accident or fire has been occurred, so that the immediate help can be given out. In surveying, you may have advantages of GPS for surveying. Accuracy requirements, you can achieve very high accuracy. You can go for control survey or radial surveys. You can see here different type of surveys we can do. In this image it is shown, and then you can see this base station with the beacon, which is transmitting the error in the study area, and this is your rover on a pole which is receiving the corrections, and this is a control unit which is communicating to the antenna through Wi-Fi or through Bluetooth. Further, very important application of GPS or GNSS is military applications. It can be command and control, search and rescue, mine laying and detection, and weapon aiming and guidance, bomb and missile guidance, artillery pointing, so forth, and GPS receiver and transmitter. Specifically, that in the defense, they throw these small miniature GPS in the enemy areas to know how the landforms are there. So this is a device which is getting the coordinates as a GPS receiver, and it is transmitting these coordinates in the space so that anybody can lock these coordinates and they can see what type of landmarks or profiles are available in the ground. Further, you can have the application in science. It can be archaeological studies, atmospheric science, and environmental studies, geodesy, geology and geophysics, oceanography, wildlife, and so forth. Recreation and sports, it can be land, sea, and air. You can see very unique application to record the path of the space air diver, and with the help of GPS, when they dive, we can keep the GPS on and it can record the path, how they are following, and they can see if there's some corrections are further required. Then for transportation in aviation, AVHS and fleet tracking, marine and space, so forth. You can see the applications of GPS system. And this we have done by ourselves as a case study for GCP's ground control point collections for Cartosat 1 stereo data. We have taken mainly the agriculture burns and the road bands to be considered here as a ground control point. This is the case of road band in the hilly terrain of Rajpur area in Dehradun. And these GCPs are basically used to process the Cartosat stereo data so that we can generate the digital elevation model, and also we can generate the geometrically correct image as an ortho image or ortho map finally. And here you can see long back we have tried to generate the one web-based word spatial information while collecting the data from mobile GIS GPS of Dehradun area. So you can see these are the field observations I've done. Further changes, if you see from GPS, the word has gone to GNSS Global Navigation Satellite System. That means we are not getting the data from a single global navigation satellite system, but from multiple global navigation satellite system. And today you can have multiple global navigation system. From one is GPS from USA, GLONASS from Russia, QZSS, which is a regional system from Japan, Compass from China, and Galileo from European country. Plus you can see IIRS, IRNSS regional system from India. And you can see here the different satellites in different constellations. For GPS, minimum 24 satellites are required. For GLONASS, 30 satellites are required. For Galileo, 27. For Compass, 330 global and 5 regional satellites are required. And parallelly, with time, people have developed a satellite-based augmentation system for different countries. This is for USA, and this is Gagan is for India, and same way for other countries it has been developed. And there are 2 regional navigation satellite system. One is QZSS by Japan. It has only 3 satellites, and which is providing the coordinate services for Japan and its surrounding. Plus IRNSS regional system for India, presently having 7 or 8 satellites, and is working for India and its surrounding areas. You can see how the plot of the IIRS satellites is there, because there are 3 satellites in this constellation which are geostationary. They are having inclination 0 degree from the equator at 36,000 kilometers, and there are 4 satellites making inclination of 23 degree from equator. And if you see their profile on the footprint on the ground, it appears to be like 8, because they are inclined at 23 degree from equator, so they are geosynchronous satellites. And if you see the concepts of Gagan, how it works, there can be different users to get their coordinates, but there are different referencing stations which are working on the known stations, and they calculate the difference every 1 second, and this difference is passed on to the master control. Master control transmit this error or difference between actual value and the calculated value in the air, and that is received by the rover or the user who wants the very accurate coordinates, and his accuracy is improved through Gagan in India and its surrounding. It has a very good application for Airport Authority of India and for defense people. Without much cost, they can get much better accuracy of around 1 meter in their data. You can see GPS augmentations in the different area of the globe. For USA it is VAS, EGA NOS from European Schengen countries, MSAS it is for Japan area, and Gagan is for India and its surrounding areas. If you see the footprint of Gagan, which is developed by ISRO, and you can see it has a very large footprint. It is covering half of Australia and half of Africa continent also. Now, if you see how these technologies are coming and developing and giving birth to LiDAR, basically LiDAR is a scanner mounted in aircraft, emits laser beam with high frequency and receives the reflected beam. So by the laser, we can only tell how much far the object is from the ground. That is direct range. So the time difference between the emission of the laser beam and the reception of the reflected laser signal is recorded to get the distance or range. And the high frequency rotating mirror placed in front of the laser converts this laser into a larger scanner, and then you can see large number of points are spread on the ground. But still, this technology is not sufficient until unless we have a DGPS system integrated with the LiDAR technology. Here you can see the base unit is here on the ground, and the rover unit is kept on the aircraft, and the path of the aircraft is calculated with respect to DGPS concept. Plus, it has an IMU which is giving you angle about X, Y, and Z. That is pitch, roll, and yaw. And this is the inertial measurement unit, which can tell you angular values about X, Y, Z, and the coordinates in the form of X, Y, Z. Measure aircraft attitudes in all X, Y, Z direction through pitch, roll, and yaw, and it can also record the coordinates. But with time, the coordinates are not so much accurate through IMU. That's why they are not recorded. And that's why the GPS is kept for the LiDAR system on aircraft. So through GPS, we can get the coordinates, and through IMU, we can get the angular rotations about pitch, about XYZ, that is called pitch, roll, and yaw. And why GPS added INS? So complementary operational characteristics of GPS can be added in INS, because INS cannot give very high accurate coordinates, and that can be replaced by GPS coordinates. INS accuracy decreases with time due to unbounded positioning errors, hence degrades exponentially with time, and that's why the coordinates from INSs are not recorded. But the GPS accuracy increases with long observation durations, and its accuracy is very high. So we use the coordinates from GPS in the LiDAR system to get the ground coordinates from the LiDAR system. So here we have to integrate together, takes out irregularities in platform orientation and gives continuous reliable solution. And this becomes self-contained solutions for the LiDAR. And here you can see there is a base stations. If we are flying at every, say, 20 to 30 kilometers, and that the rover is kept in the aircraft with INSS, with IMU, and the GPS data recorded in air and on the ground as a base and rover every 25 kilometers determines the aircraft position, and IMU record the attitude variations for in pitch, roll, and yaw of the platform for carrying out attitude corrections for the laser beam. It developed the 3D points consisting of lat long and elevation of points on the ground based on aircraft position in the form of lat long and elevation, aircraft orientation in the form of pitch, roll, and yaw or heading, plus scan angle and round trip propagations time of laser pulse. That means how much, what's the direct range from pulse from the LiDAR sensor to the ground. While integrating all these three data sets, we can get the ground coordinates through LiDAR technology. So you can see in this diagram how it is coming up. And overall, if you see in the case of GPS, why the word has gone from GPS to GNSS. That means if you use the receiver, it is GNSS enabled receiver. That means it is using the constellation from, or the satellites from different constellations. And specifically when you're working by GNSS in a very narrow lane, then what will happen? You can easily get sufficient number of satellites, and you are never lost by minimum number of satellites requirement. And or if you're working in a very dense canopy of forest, still you can get large number of signals, and every time your geometry is very good. So you don't have to wait that when is my geometry is good and to record the data. So these are the advantages when you go for GNSS system in place of GPS system. And you can basically, it is ideal interpretive, allows navigation with one signal, each signal from a 4 or more system with no additional receiver cost or complexity, right? These are a few references you can refer by GPS positioning guide, Geodetic Survey Division Canada, and GPS Tutor we have developed long back. And you're right. Thank you for listening me in this series of core lectures. And if you have questions, please let me know.